So hopefully this gives you a clear sense of the challenges we hear and how touchless forecasting and forecasting as a service helps. Let me just deep dive into exactly the kind of models that we considered in this round phase 2 with NVIDIA. So obviously, and this should not be news. Most folks that have used IBP or implement IBP should know this. These are all the models that SAP IBP has. Some good performance comes from ARIMA, auto exponential smoothing, gradient boosting. A challenge we are seeing with COVID patterns is the level of intermittency in the data is increasing. You have a lot more blanks in periods because either supply constraints or demand issues and inability to distribute and so on. So now intermittent forecasts have always been a very hard thing to crack, right? Most forecast models seemingly work much better when you have a value in every time bucket, but when you start to experience a lot of intermittency and blanks is where things start to break down. So this is where we on NVIDIA Kratos cloud compute platform, we deployed another, our data science team essentially wrote gradient boosting with Python and in Jupyter Notebook, deployed it on Kratos, and also deployed other models like CatBoost, Random Forest, Forecast. And then you also think about GitaCloud forecasting service that we are going through a lot more models and really optimizing the ML hyperparameters and saying what's the best possible forecast. We called it external forecast because that's coming in from a third party into your environment, but that's another competing forecast, if you will. And then of course we had the human inputs, right? Both from sales and demand planner. Remember, Anthony talked about the NVIDIA process of sales provides the bottoms up view of the forecast across their accounts, and then demand planners judge it, working with BUs, and there are kind of two versions of demand planner forecast, if you will, constrained and unconstrained. But all of this is coming into what we then refer to as a touchless forecast. Right? So let's now just try to understand exactly how the touchless forecast works. Before we go into it, I just want to make sure from a forecast basis perspective, everyone's clear that we had choices. We had both the booking history and the shipment history. We just always, as a best practice, want to forecast the unconstrained demand, which is bookings, which is customer requested quantity and dates, not shipment history. You can forecast that too, but essentially you're baking in all of your supply distribution constraints, right? So that's not a true representation of demand, although shipment history and shipment forecast becomes important because that's directly linked to the revenue forecast. So you can see here a trend across quarters for the data, and you can see how in the initial, and these are fiscal periods. I'll explain NVIDIA's fiscal quarter in a minute, but you will initially see a lot more bookings meeting shipments across quarters, but see how this pattern changes in 2021 and 2020. So a lot more supply challenges coming. So NVIDIA fiscal calendar goes February to January. So you can think of it as when you're talking about Q1 of 2023, that's essentially Feb 2022 as a calendar month onwards. So Feb to April is the Q1, May to July is the Q2. So from the experiment that we conducted, we were provided data in the past, right, across all the bookings and shipment history throughout, and then the user forecast. We then chose to forecast Q1, Q2, Q3, and Q4 of 2022, which is sort of all in the past. So that's the booking history data we were provided. Of course, NVIDIA has data on Q1 and now Q2. We deliberately did not collect all this data. So if you understand how we are forecasting in monthly cycles and in monthly buckets, but then we are aggregating it up into quarters. And the reason being that when planners are measuring error at NVIDIA, they are basically saying it doesn't matter if I forecasted 100 in month 1 and 110 in month 2, and actuals come in differently, right? If actuals come in, for example, 95 and 115, to them, it doesn't matter. If overall quarter is what they're looking to say, well, no matter when sales happen, my guidance to the street is in quarterly buckets. So I want to measure error in quarterly terms also. So we started the experiment in what you would think of as the previous quarter, last month of that, fiscal month 12 happens to be January 21 calendar month. That's where we forecasted the first cycle, and we got sort of 4 quarterly values across the 12 monthly numbers, right? We refer to this as quarterly leg 1, leg 2, leg 3, and leg 4. We then move forward in time, and now we are able to, as if we are sitting in April 21 calendar month or the last fiscal month of Q1, we forecast the next 4 quarters again, and you can see how the time axis shifted. So 3 of the quarters we have numbers from before, but now we have a new quarter being forecast. Again, as we drive the clock forward and we're now sitting in July, we can now say, well, again, let's forecast the next 4 quarters and do this one more time. And now you can see what's happening for a given quarter like Q4. You have quarterly leg 1 in this latest iteration 4, the FM9 cycle. You also have a leg 2 view, a leg 3 view, and a leg 4 view, right? So we are able to now see 4 different forecast numbers, 600 when we were sort of 4 quarters ahead, 660, 3 quarters ahead, 630 and 690. And this is what we refer to as legs. It's just very important. I wanted to make sure, I'm sure many of you get this intrinsically, but for folks that are not familiar, these are quarterly legs we are looking at. And this is our way of saying, well, just a quarter ahead versus 2 versus 3 versus 4, what was your forecast and what was the actual? So we measure error against the actual bookings in that quarter, 680 against these 4 quarters. So hope this is clear. I'm going to move on. So as you can imagine, we are sitting in let's say Q4 2021 last month and forecasting the next 4 quarters. It gives us, from an IBP best fit forecast perspective, leg 1, leg 2, leg 3, and leg 4 forecast. We also, when we are, let's say, at this point in time, and we now have a sense of actually what happened in the quarter and what did you forecast, we're able to measure the error in that leg 1 forecast by comparing it with the booking history. When we move the clock further back in time and we have booking history for Q2 as well, we are now able to see how the leg 2 IBP forecast was 2 quarters ahead versus what bookings were. And you can imagine this leg 1 error versus leg 2 error to be different values, because the further ahead you're looking, the more likely you are to be wrong. We do the same with a naive forecast, which is simple moving average over the last 3 months. This is our way of saying, well, and you'll be surprised given the level of volatility. Sometimes the naive forecast is pretty close to or meeting some more sophisticated models, because it's just the trends are too volatile and fragmented. So what we do from a forecast value add perspective, we take the IBP forecast, the naive forecast, we compare the two to say, well, how is IBP forecast helping? How much more accurate or how much less error is IBP producing? So the way we measure forecast value add is the naive error minus the IBP error. And you can imagine we do this for leg 1, we do this for leg 2. So now we have a leg 1 FVA and a leg 2 FVA. Similarly, we'll have leg 3 and leg 4. You can see this with some data. Before I jump into the data, just understand the SKU level absolute percent error, APE. We are taking the absolute of the forecast minus actual and then dividing it by actuals. Now, obviously, with intermittent series, when you have no value to report in actuals, you get a divide by 0 problem. So we basically say if either the forecast or actuals are blank, but not both, we count the error as 100%. Either you forecasted, didn't sell anything, or you didn't forecast, you did, well, the error is 100%. So this doesn't inflate the overall error, but it gets away from the divide by 0 problem. Also, if both forecasts and actuals are blank, then of course we say, well, you forecasted nothing, you're selling nothing, so you're 0 error. And with this approach, we are not limiting the error to 100%. It can be 200, 300, 400, 500%. So we try to get a true sense of the error, because the more wrong you are, the supply chain is building all those materials, the cost to business is high. So we don't just report accuracy as one minus error, we report error and let it be unbounded. So let's get back to this. Let's say for a given SKU 393 in Q4 2022, and this is fiscal Q4, if they sold 19,200 units and leg 1 IBP forecast was 19,780. So you can see these two numbers here. The absolute difference is 580. So IBP obviously did really well forecasting it. 580 divided by 9,200 is 3% error. You can see it here. That's leg 1. If you look at leg 2, IBP had forecasted, meaning 2 quarters before, IBP had forecasted 2652. And given that error is slightly more than 3%, it's 8%. So you can see how the error is kind of growing, the more in future you're looking at. The higher the lag, higher the error in general. Also understand that that's SKU level absolute percentage error. We are doing a weighted MAPE across all the SKUs at a higher level. So if let's take a product group PG1 as a simple example. If you have two SKUs, 318 and 393, and both have sold certain quantities, and you can see for leg 1, SKU 318 is 18,500 is sold with 6% error. The other 393 sold 19,200 with 3% error. So we are essentially doing a weighted error with the actual booking quantity, booking history being the weight that is being applied. So with this approach, if something is selling a lot and has high error, then obviously that error counts. If something is selling very little, has high error in the larger scheme of things to the business, it doesn't matter as much. Now, we do have the ability to also see the unweighted raw error averaged at higher levels, but I'm just showing you the weighted MAPE. So essentially, you can see for leg 1, across the two at product group level, the weighted average error is 4%. You can also see this for leg 2. Leg 2 is the history remains the same, obviously, but error, as you can see in IBP, was much higher, 44% at leg 2 in this case, and 8% for this other SKU. So when you combine the two, you get 25%. So now this is a clean way of understanding your weighted average error across leg 1 and leg 2. Hope this is clear. So I'm going to move on. Remember, I talked about the forecast value add as the naive forecast error minus the IBP error. So for the same SKU, if you look at what is the IBP error, you can see that naive forecast was 49%, IBP error was 3%, and hence the difference between the two, 49 minus 3, you get the IBP leg 1 forecast value add as 46%. Obviously, there will be a leg 2 forecast value add and leg 3 and so on, but this is one way of understanding that when naive forecast is showing less error, this forecast value add actually turns negative. And that's how we alert and alert the planners to say a certain part of the process is not functioning. So now that hopefully you've clearly understood the quarterly lag concept, the weighted MAPE concept, and the forecast value add, let's look at the actual results across. And this is a subset of SKUs. We are not reporting data for all the SKUs, but for this subset, you can see, and just so everyone's clear what these bars represent, this last gray bar is the naive error, right? The naive forecast error. And this, we are reporting the leg 1 error in fiscal quarter 4 of FY 2022. The naive error was 121%, obviously the highest. And most of the times we observe that. We have the demand planner forecast error here, which is really good. You only see 81% error compared to the 121 in naive. The Kratos XGB, the extreme gradient boosting error is here. It obviously has much higher error. IBP forecast error is somewhere here. It's better than Kratos XGB across the board, but the demand planner obviously has more insights into the business and they're doing better. And sales forecast error, external forecast, which is GitaCloud service. And you would notice that this external forecast error is 78%, so it's doing really well across. There are some other models like GetBoost and Random Forest and so on. So all of those are represented here. So I know this is a lot of data to absorb. So hopefully you can correlate the colors and the numbers and get a sense. So that's the error. If we look at the forecast value add side of it, you can essentially, the same colors are represented here, so easy to color code. So just think of compared to the naive error, which is 121, demand planner was 81, 81 versus 121, you're looking at 40% value. If you look at IBP, it's got 21% value add. In Q4, you can see that this is the Kratos Standard Forest 25 or Touchless Forecast 31, that they're doing better. But in general, you can see in all the machine learning signals, the Touchless Forecast has done the best. When we looked at the average error across the quarters, so this is a picture for you to understand from Q2, Q3, and Q4. If you go across the three, and we took an average, again for leg one, the numbers are now slightly different. The Touchless Forecast value add is 15%. It's almost matching the demand planner value add. So without any insights into the business, it's able to come very close or look at the other way, all the machine learning signals. The external forecast from GitaCloud is at 10%, IBP is at 5%, some of the other models are 3, 2, and 3. So the Touchless Forecast, which is taking the best input from all the forecasts, is just simply outperforming. So that's, in a nutshell, the value add supported by data. Let's talk about exactly how we are generating the Touchless Forecast. So remember, I spoke about if you're forecasting a given quarters and 4 quarters ahead, so you have leg 1, leg 2, leg 3, and then leg 4. So if you are at this point in time in January 20, and you forecasted Q4 2021, you will have a demand planner leg 4 forecast, Kratos, IBP, sales, and so on, right? When we look at the forecast value add across the board, we compare, and let's say we found the external forecast value add to be the highest. Then we record this as a FVA winner for this quarter for leg 4. If we dial back to Q1 and we say, well, just 3 quarters ahead, now all these are leg 3 value adds, right? Again, compare and say, well, who won? Who's the most accurate 3 quarters ahead? And let's say in this case, Kratos Cat Boost turned out to be the most accurate, adding the most value. So you just now can clearly see that leg 4, external and Kratos and IBP, this is how you're getting different. When you're looking at these leg 1, 2, 3, and 4 winners, demand planner, IBP, Kratos, and external, you're looking at now in the Touchless Forecast, taking the demand planner forecast in leg 1 and using that for your first quarter. Leg 2, taking your IBP forecast and putting that as your second quarter. Taking the leg 3 Kratos and putting that as your third quarter. So what you're doing is, instead of saying any particular forecast across the 4 quarters, you're taking in a quarter specific way the most accurate forecast. This is how we generate the Touchless. And obviously, as we move forward in time, you can see different winners emerging in different legs, sometimes the same winner, sometimes different. And that's how we keep generating. And this is all being done for SKU 1. We can also see that we're doing this for SKU 2. You may get completely different winners. The idea is that every cycle, every quarter, every SKU Touchless forecast is being optimally blended. So this is just, in the interest of time, going to go through some of these slides really fast here. Leave some time for Todd and for Q&A. But the FVA winner, you can see, in this case, demand planner was 1. So we select that as 1, Kratos as 2, because that's the highest FVA, we set that as 2. In this case, IBP was the most accurate in both cases, in Q3 and in Q4. So we are selecting the value 3. And that's how the Touchless forecast is coming together. So when you're looking at SQ393 for leg 1, we just say, well, in this case, naive forecast 1. So we just grab the value of naive forecast into the Touchless, right? 16,828. In this case, the demand planner was the most accurate. So leg 1, take 13,510, drop that into the Touchless forecast. See how this behavior changes when you are in leg 2. Leg 2, you're going 2 legs out. So when you are naive forecast being the most accurate, you skip and say, well, what was the naive forecast 2 quarters out? grab that into the touchless. Here you see IBP was the most accurate. So we go 2 quarters out, take the value in IBP forecast and put that into touchless. So hope this is clear. This is the last point I wanted to make. We also have like a FVA heat map to say, well, at a SKU by SKU level, who's winning most often. And if you think of these numbers, 1 being demand planner, 2 being creators, 3 being IBP, 4 sales, 5 external, so on. You can see in Q2, IBP is winning a lot of SKUs, right? Where it is simply the most accurate signal. In some cases, you can see the naive forecast winning, or in some cases, other models are winning. But this pattern you can quite clearly see when you go from Q2 to Q3, it changes rapidly, right? So now there's a lot more ones in the picture, meaning demand planners more accurate, many more SKUs. So this is the dynamism in the data. And this is why you just can't scale this manually. You have to have an automatic approach every quarterly cycle. When you look at the average across Q2 to Q4, you see a decent number of cases where demand planners done the best, and that's expected. But also in a decent number of cases, IBP is doing very well. And then there are cases where the other models. Okay, so let me just wrap this up in terms of the key takeaways. We want you to have, we are able to generate an accurate demand signal at granular levels autonomously. Keep in mind, different models outperform in different horizons. So we cannot just take a weighted average approach and just plan 10% of everything across all the quarters. That's not the way to value. And we are able to provide planners control, meaning the touchless forecast we generate, they're still able to override it in some exceptional situations. We track that if that helps or not. So this approach is very flexible, leaves planners in control, allows for very easy ingestion of additional human or machine signals. Right? In the end, you get a much lower error and a much higher planner productivity. They don't have to struggle with blending as a process for everything. So hope that was clear.